Hi, thanks for joining me. Today I'm going to be talking about two really important theorems in geometry, both of which concern triangles. Firstly, Stewart's theorem and the cosine rule. I'm going to state both of them and then I'll get on to their proofs. Okay, so Stewart's theorem, we're going to have a triangle like so, and it has three sides, of course, A, B and C. I haven't labelled this one A. Okay, so this length here has length A, this one B and this one C. Then what we're going to do is draw any cvian onto the side length A. So what that means is we take the length, the vertex opposite the side A, i.e. this vertex here, and just drop any line we want onto this edge here. Of course, I've drawn this cvian here, but equally I could have chosen that one, for example, or any one of the other infinitely many. Okay, then what we do is we call this sort of bit of A here, which is next to C, little m, and then this other length here, little n. Okay, and then what we have is this equality here, b squared times n plus c squared times n equals a times d squared plus mn. Okay, so that's Stewart's theorem. Now let's talk about the cosine rule. Similar sort of thing, we have a triangle like so, and I've used different letters to this one here to avoid any ambiguity. Okay, and we have E, F and G being our side lengths, and then the angle opposite the side length, little f, I've called capital F. Then we have this quality here satisfied, so little f squared equals e squared plus g squared minus 2eg times cosine of capital F. Okay, so that's the cosine rule. What I'm going to do is now prove both of them, and to prove Stewart's theorem I need to know the cosine rule, so it makes sense for me to prove the cosine rule first. So let's prove the cosine rule and then we'll get on to Stewart's theorem. Okay, so to prove the cosine rule, let's draw some things onto this diagram here. Firstly, let's drop down a line from this vertex here all the way down to this line here, and that meets it at a right angle. Great. Now let's call this length here h. Okay, and we'll call this length here I. Okay, now basic trigonometry, cosine of f is adjacent over hypotenuse, so that's going to be I over g. Okay, but of course, multiplying both sides by g gives us that g cosine of f equals I. Similarly, sine of f is opposite over hypotenuse, so that's h over g. Okay, and again, multiplying by g gives us that g sine f is equal to h. Okay, great. Now let's use Pythagoras' theorem on this right angled triangle here. Okay, so that gives us the h squared plus the length of this line here, which is going to be e minus I squared. Okay, and that equals f squared. Okay, and hopefully you can see that it's already starting to look like what we want. We've got an f squared on one side, we've got an e squared coming out there, and then we're going to be able to manipulate the rest of this to give us the g squared, and then this term here. Okay, so let's expand out this bracket here. So h squared plus e squared minus 2ei plus I squared equals f squared. Okay, what's h squared? Well, that's g squared sine squared f. Then I squared is g squared cosine squared f. So h squared plus I squared is going to be g squared times sine squared plus cosine squared of f. But of course, sine squared plus cosine squared is 1, a very standard trigonometric identity. So h squared plus I squared is g squared. Okay, that's great. So let's replace that with plus g squared. Okay, so we've got g squared and the e squared there. What remains to show is that this thing here is 2eg cosine f, but that comes right from this thing here, swapping the I for g times cosine f. Okay, so let's just write it out as we want. So we've got the f squared from there equals e squared plus g squared. Then this thing here is minus 2e g cosine f. Okay, and then we are done. That's the end of the proof for the cosine rule. Okay, now let's use this cosine rule to prove Stewart's theorem. Okay, so the proof for Stewart's theorem is essentially a direct corollary from the proof of the cosine rule. And what I'm going to do is call this angle here theta, and then apply the cosine rule twice. Once to this triangle here, and once to this triangle here. Okay, so first let's look at this triangle here, the big one. Let's apply the cosine rule. So we get the length opposite theta, so b squared is going to be equal to this length squared plus this length squared. So d squared plus n squared minus 2dn cos theta. Great. Now let's use the cosine rule on this triangle here. So this angle here will be precisely pi minus theta. Okay, so the same thing, the length opposite pi minus theta, so c squared is going to equal this length squared, so d squared, plus this length here squared, so plus m squared, minus 2dm cosine of pi minus theta. Okay, but cosine of pi minus theta is minus cosine of theta, so I can write this as plus 2dm cosine of theta. Okay, now what I want to do is sort of add these two equations together to get rid of this cosine term, because you can see here there's no cosine involved, but I can't do that because you've got an n there and an m there. But to resolve that problem, what I'm going to do is multiply this top equation by m and the bottom equation by n, and then I can add them up, and I'll have 2dmn cos theta there and 2dmn cos theta there. So when I add these two equations up, they'll cancel. Okay, so let's do exactly that. Let's multiply the top equation by m. So I get mb squared equals md squared plus mn squared minus 2dmn cos theta. And the second equation I'm multiplying through by n. So I get nc squared equals nd squared plus nm squared plus 2dmn cos theta. Okay, and as I said, I'm going to add these two equations up, and then we're pretty much done. mb squared is that thing there, plus nc squared is that thing there. So b squared times n plus c squared times n is equal to, and then on the right hand side, remember these two things cancel, which is what we want, and we're just left with md squared plus nd squared. So that's d squared times m plus n plus mn squared plus nm squared, which is mn times m plus n. Okay, and you can see what we're going to do now. Use the fact that m plus n is precisely the whole length a. Okay, so that's d squared times a plus mn times a, and then we can just factor out the a, and then that equals a times d squared plus mn. Okay, so a nice neat little theorem there. Oh, my whiteboard is just fallen. Let's hope it doesn't fall again. Okay, so Stewarts Theorem, a nice little proof which comes essentially directly from the cosine rule, and this one here doesn't involve any cosines, which is quite nice, and also it works for any arbitrary Cevian that you draw. I hope you have enjoyed this video. Perhaps you have seen the cosine rule before, but maybe not Stewart's theorem, but I thought I'd include the cosine rule in this video because it's more general. Anyway, if you are new here, please do consider subscribing. I make lots of videos like this, ones in which I prove theorems, ones in which I explore cool bits of maths, and some in which I do some problem solving as well. So, all around, lots and lots of fun maths. But yeah, anyway, I'll catch you in the next one. Have a great day.